Well, hello everybody. So, we are going through the module on distillation, and we have already discussed the simplest type of distillation, which is the flash distillation. We have discussed the basics of flash distillation, and we have also solved a problem on it. And after flash distillation, today we are going to discuss the fractionator, which is the most commonly used distillation column in industrial practices. So, the basics or the introduction of the fractionator was already introduced to you in the last class, where you had seen that in the fractionator we have, this is a continuous multi-stage process, right, and in this particular multi-stage process, and each particular stage, it is provided either by plates or trays inside the column. We can have such plates or such trays. We can also have some packing sections, right. So, therefore, in between two packing sections, the feed is introduced. So, it can either be, the stages can either be provided by means of different stages or by means of different plates or the trays, or we can also have some packing sections which provide the equivalent number of stages which is required for the required separation that you wish to achieve from the feed of flow rate F and composition XF to a distillate of flow rate D, composition XD, and a bottom products of flow rate B and composition XB. Generally, we find that this XB, XD, XF, they denote the composition of usually the more volatile component or at times the desired component. And the product, as I have already mentioned, the product specification, it is specified either in terms of product purity or in terms of recovery, amount of recovery, right. So, therefore, for the time being, we will be discussing regarding the tray towers and the details of the inside of the trays, etc. They will be discussed separately after we have discussed all the different processes, say distillation, absorption, adsorption and liquid extraction. Then we will take up a unified approach to discuss the trays or the plates as well as the packings inside the tower. For the time being, we will discuss the entire layout of a fractionator in its simplest form and what are the other additions that we require in industries. And once you have learned this, we will go for design of the fractionator column. Now, in the simplest form, what we have, I have already given the basics. You must have a feed, you must have a distillate which is drawn from the top, you must have a product stream which is drawn from the bottom or the bottom product stream. So, in the minimal arrangement, you must have an arrangement for introducing the feed. It's a huge column, you just cannot think of pouring the feed inside the column. So, there should be some arrangement for enrichment of the feed. As I had mentioned in my previous lectures, the section above the feed, this is known as the enrichment section. The section from the feed to the top tray. And again from the feed to the bottom tray, this section, this is known as the stripping section. So, therefore, what are the things that you need to discuss or you need to know about a column? You need to know the arrangement for the feed entry, you need to know the details of the enrichment and the stripping section. Usually both the sections, they are having the same arrangement, more or less the tray types, etc. The column diameter is uniform throughout, unless we have a very large column and it will be economical to go for a different diameter for the enrichment or the stripping section, we do not go for it. After that, we need some particular arrangement for the top product collection. And we also need some particular arrangement for the bottom product collection and also the introduction of the vapors in the stripping section to bring about the mass transfer in the stripping section. Just like we need some amount of reflux from the reflux drum into the top section in order to bring about enrichment in this particular section. So, we are going to discuss one by one. First, we will be discussing the overhead system, then we will be discussing the bottom section, and finally, we will be discussing the feed entry zone. Now, normally we find that we have a total condenser. What does a total condenser mean? A total condenser means that the entire vapor which is coming out from the top of the tower is condensed in a total condenser, and only liquid it goes out from the total condenser and it collects in a reflux drum. These were definitely touched upon in the previous class, but I am repeating it once more just for your convenience. And from the reflux drum, what happens? We take out some amount of the product as the distillate. As I have mentioned, it has the composition of D and XD. Usually from the total condenser, the liquid it drains by gravity into the reflux drum. So, usually the reflux drum is kept at a lower elevation compared to the total condenser, so that the liquid can drain here, it collects here, from the bottom it is taken out, a portion of it is taken out as distillate, and the remaining portion it is refluxed back into the column, say at a reflux flow rate R. Definitely, as you can know, the composition of the reflux is XD. So, therefore, this reflux is again introduced back above the top tray of the column. Now, definitely the liquid has to be pumped out from the reflux. You can either use a common pump as you have done in this case. It can also be that you have two different pumps for the distillate as well as for the reflux. And the pressure which is developed by this product pump, what does it need to overcome? It needs to overcome the pressure drop in the piping, the heat exchanger or the condenser, and also the liquid head in the product storage tank or the reflux drum. One more thing also, just for your clarification or just to remind you, can you tell me what is the heat which has to be removed in the total condenser? Definitely some amount of vapor is coming and you need to remove heat such that the entire vapor condenses into the liquid phase. Now, from the column top, under what condition is the vapor exiting, can you tell me? The vapor which is exiting from the column top, definitely that is at its dew point. So, therefore, this vapor is at its dew point, it gets condensed in the condenser and enters the reflux drum. Under what condition? This has to be liquid at its bubble point, isn't it? The vapor which enters the condenser is at its vapor which is entering here, that is at its dew point. The liquid which is exiting from the condenser, that is at its bubble point. So, therefore, what is the amount of heat that has to be given to the condenser by the cooling medium in the condenser? It has to be the latent heat of vaporization of this particular vapor stream in order to change it from its dew point, to change the state of the top product from its dew point to its bubble point. Now, this is one thing that you need to remember when you will be sizing the condenser, and that is specifically why I have mentioned you this particular point. Now, in the reflux drum, if you observe, you will find that in the reflux drum, what happens? The liquid, it accumulates in the reflux drum. This liquid level, it should be controlled, or else definitely it is going to overflow, we cannot allow that. How do you control the liquid level? This liquid level is controlled by controlling the distillate flow rate. You can find that we have a control valve in this particular case. By means of this control valve, we control the distillate flow rate, and based on this control, the liquid level in the reflux drum is maintained. One other thing is very important. See, you have started with a feed. This feed had been taken up from some storage tank or something. So, there is always some dissolved gases in the feed. It was definitely exposed to atmosphere. Moreover, particularly in vacuum columns or in subatmospheric columns, you cannot avoid some sort of leakages into the column. The leakages, it can take place through the flanges, through all the fittings, etc. There will be some amount of leakages, and this non-condensable gas, that is also carried away along with the vapor. So, all these non-condensable gases, they pass through the condenser and they come into the reflux drum. In the reflux drum, we find that naturally as the liquid starts accumulating, the non-condensable gases, they will be accumulating over the liquid in this particular space which I have shown here. Now, if you keep on allowing this particular non-condensable gas to be accumulating here, then definitely there is going to be a pressure build up. So, momentarily we need to vent or to bleed out the gas from the reflux drum in order to avoid the pressure build up, right. Now, there is another very important purpose of this particular bleed that we use. Just one small thing, I will just digress and tell you that more or less for the bleed or the vent, the arrangement is the same. When we vent it to the atmosphere, we call it a vent, and when we direct it to some flare, we call it a bleed. The arrangement for venting or bleeding the gas, it is the same. Well, now coming back to the point, the other very important purpose of bleeding out the gas from the reflux drum. Just try to understand this. From the condenser top, the vapor moves out. This moves by means of a overhead vapor line. Usually, as during the discussion on flash distillation, Professor Ray had mentioned that usually these vapor lines, they are oversized, right, so that the pressure drop is much less, and from there it goes to the condenser. In the condenser also the pressure drop is very less. So, therefore, what we do is that normally by regulating the bleed, we control the column top pressure. So, therefore, the purpose of the bleed is twofold. Firstly, as I have said, that it avoids pressure build up, and the other important thing is it regulates the pressure in the accumulator, and therefore, as a result it fixes the column pressure here. Why do you need to fix the column pressure? What are you doing in the column? We are performing a distillation. We assume ideal stages. In ideal stages, what do you have? You have the products which are leaving to be at equilibrium with one another. So, before you do anything, you need to construct the equilibrium curve. Under what conditions will you construct the equilibrium curve? It will be at the column pressure. Whenever you talk about the column pressure, it is the top pressure. So, remember one thing, the top pressure, when you mention the column pressure, it is generally the pressure at the top. Quite naturally, it is quite evident the pressure at the top and at the bottom will not be the same. It will be depending upon the number of stages that you have inside the column. It will also depend upon the liquid level inside the column. So, therefore, if the column pressure at the top and bottom are not very different, under that condition we can take up the column pressure or we can take up an average pressure, and on that pressure we can generate the equilibrium curve, and we can use the alpha value corresponding to that particular pressure, and we can use this. This is definitely one thing. Suppose you find, this will be discussed in greater details in the next class, suppose you find that the pressure at the top and the bottom are very different, then the conventional approach is you select the alpha corresponding to the top pressure, select the alpha corresponding to the bottom conditions, and generally root of this is the alpha at which you generate the equilibrium data. So, therefore, when the pressure variations are quite high, then you need the pressure at the top, at the bottom, and definitely also at the feed section. So, therefore, the other important purpose of this vent is definitely to regulate the pressure in the accumulator, which in turn fixes the column pressure. When you have got a vacuum column, then in that case, in order to maintain the vacuum, you need ejector or vacuum pumps, they create the vacuum. For such columns, the same arrangement is used to remove the non-condensable from the column. And in this case, as I have said, that leakages are inevitable, and therefore, it is very important that the non-condensables are vented out, right. And when you are going to select the column pressure, as was discussed for flash distillation, the same thing applies here, that unless vacuum is a necessity, we will not go for pressures much below the atmospheric pressure. We would like to maintain the pressure at about slightly above atmosphere to see that there are to minimize the leakage things. Next comes the column top temperature. Remember one thing, since we are having a non-condensable, so therefore, in this case C equals to 3, and for a binary mixture, or else C equals to n plus 1 if there are n number of components. So, both the column pressure and column temperature, they can be independently varied. How do you control the column temperature? See, the column temperature, it directly relates to the distillate quality, because if you need a higher purity distillate, what do you need? You need to have a higher amount of reflux. When you have a higher amount of reflux, quite naturally the column temperature, it goes down. So, therefore, the column top temperature directly relates to the distillate quality, and it is also easily monitored. You can just have a thermocouple on the top. So, therefore, the overhead temperature, it is controlled by manipulating the reflux flow rate, which in turn fixes the distillate quality. The detailed PNID of the overhead system, the bottom system will be discussed in the next class. So, I am not going into the details of this. There is one thing that you need to remember. There can be a situation where it is required that the top product from the column is desired as a vapor. When it is such, then what happens? Then there is partial condensation of the vapor in the condenser, and the vapor liquid mixture under that condition enters the reflux drum, and in this reflux drum the liquid separates, and with the same arrangement that was done for the non-condensables, the vapor product is withdrawn from here, and this is the product. The liquid, either the entire liquid can be recirculated as the reflux, or part of the liquid can be withdrawn as a product depending upon the need of the customer. In industry parlance, what it said is that when no liquid product is withdrawn, under that condition they specify it as the no reflux condition, but this is a misnomer. In textbooks and in distillation, as we know it, when no product, either liquid or vapor, is withdrawn from the reflux drum, that corresponds to the condition of the total reflux, that corresponds to the condition of total reflux when neither the vapor product nor the liquid product is withdrawn, and so therefore, we will be referring to the total reflux condition when we do not withdraw any product. Now, one more thing also you need to remember, that is that when there is partial condenser in the partial, when we use a partial condenser, under that condition quite naturally the vapor, it comes out from here and it gets partially condensed. So, the liquid and the vapor, they are in equilibrium in this particular case, and therefore, this corresponds to or rather we consider this as a one single vapor liquid contacting stage. So, under this condition, when we have calculated the total number of stages, we need to remember the actual number of stages has to be less by 1 for accounting for the partial condenser. We will see that we also have one stage in the reboiler, which we will be seeing later. So, therefore, there is another thing which I would like to mention before I go ahead with the bottom section. Tell me one thing, the reflux, it is withdrawn and the reflux is dropped here. What do you think, that you will just have a nozzle and the reflux will be poured and then it flows across the column? If that happens, then what do you expect? Moment the reflux enters, it meets the vapor, it cools the vapor, some amount of the more volatile component will be transferred to the reflux. Definitely the quality of the product will decrease. The other thing is, moment the vapor comes in contact with the cold reflux, there is an abrupt contraction. This may result in vibration or maybe some internal hammer inside the column, which is not a desirable situation. So, definitely we try to, it is important to ensure that the reflux does not come in contact with the vapor moment it enters here. So, for that case, what arrangement do we make for this? For that case, just above the reflux entry nozzle, we have a horizontal baffle here, and we have a false downcomer in this particular case. This is known as a false downcomer. So, the reflux, it enters from here, it flows down, and then from beneath the false downcomer, it meets the liquid on the tray. From there it flows, it meets the vapor which comes up through the tray, mass transfer occurs, and then just like all other tray, the liquid, it flows down to the next tray. Now, there can be several other variations of the overhead condenser. For example, we can have a condenser subcooler where we cool the reflux, so and then introduce it so that the requirement of reflux gets less. We can also have a hot reflux arrangement. We can have a condenser with hot vapor bypass arrangement as well. I am not going into details of all this. It is just to mention or to make you aware that such things are there. If you would like to have a greater clarification regarding these designs, etc., we will definitely take it up during the interaction sessions, and we will be happy to clarify or would be happy to discuss these things during the interaction sessions. Now, let us come to the column bottom section, this section between the bottom tray and the bottom here. Just like in the column top section, what do we have? In the column top section, we have a reflux. This reflux is a liquid which is richer in the more volatile component. So, therefore, it comes in contact with the vapor, there is additional mass transfer, and for the interface mass transfer and greater enrichment, the reflux is masked here. Same way, we also need a vapor reflux from the bottom tray, or rather vapor reflux in the stripping section, so that it comes in contact with the liquid which is falling through the trays, and so that there is interface mass transfer here, and through this we can get enrichment in the stripping section. How is this particular vapor generated? What we do, from the column bottom we withdraw the liquid product, and then that is sent into the reboiler, and this in the reboiler what happens? There is partial vaporization, and we have a liquid vapor mixture in equilibrium with one another. The vapor, it is introduced in the column. Where is it introduced? It is introduced just beneath the top tray and above the liquid level at the bottom of the tray. So, that this vapor, it comes in contact with the liquid at the bottom tray, and the stripping of the more volatile component starts from this particular part itself. This reboiler, it is nothing but a heat exchanger. What is the amount of heat that it has to give? Definitely the liquid which is coming from the bottom, that is at its bubble point, and the liquid which is the vapor which is going out from here, that vapor and the liquid which is coming out from here, they are within the liquid vapor zone. Agreed? So, therefore, the heat which has to be provided has to be from the liquid at its bubble point to the position where in the inside the two phase zone where this point lies. So, that is the amount of heat that has to be provided. What provides this amount of heat? It can either be some condensing steam or any other hot streams which are available in the pipe, in the plant can be used. Now, using this available hot stream, naturally what it does, it improves the plant economy by saving both the hot as well as the cold utility. The hot streams had to be cooled before they had to go for storage or for some other use. The liquid from here had to be heated. So, if you can use that hot stream to heat the liquid, naturally it saves the hot utility required for partially vaporizing the bottom product, and it also saves the cold utility which is required to cool the hot streams from the plant. These reboilers, they can be of different types. The reboiler which is shown here, this is the kettle type reboiler. We also have the thermosiphon reboiler. For small distillation columns, we can have fired furnaces, but that is not very common. For viscous products, what usually happens is that we have a pump, the pump, it draws out the liquid from the bottom, forces it through the reboiler, and then the hot product, a mixture of vapor and liquid is introduced in the column, and here it flashes to give the required vapor. This is known as a forced circulation reboiler. Again, I will not be going into details of the design of each of them. Two things are important for reboiler sizing. You need to know the heat load. If you are interested to know more about the types of reboiler, again during the interaction sessions if you wish, then we can give you some insights or some references from where you can get the details of those. One very important thing which you should remember, it can always happen that the product which you are getting from the bottom is at such a temperature that it will degenerate or it may crack at temperature slightly above the bottom temperature. A classical example is that of a crude distillation column. In the crude distillation column, what do you have? We find that in the crude distillation column, the bottom product is a reduced crude. Usually it cracks at around 400 degrees centigrade. Typically the bottom temperature is about 365 or so degrees centigrade. So, when this will be introduced in a reboiler, quite naturally the reboiler temperature has to be close to 400, it may be slightly above it. So, therefore, what happens? Coke formation happens, and there is coke deposition in the pipelines as well as in the reboiler surface, in the equipment itself. We cannot afford it. So, for such cases, what do we need to do? We cannot use a reboiler for such cases. So, for such cases, what we do is we introduce steam under superheated conditions. Point is, you can use any other liquid, but that has to be immiscible with the liquid which is there inside the column. Normally, since I am talking with respect to hydrocarbon columns, so we use steam stripping. But the important part is that the steam that I use is superheated and it is immiscible with the liquid which is there. The steam is again injected just like the vapor, just below the bottom tray and just above the bottom liquid level which is there. What does the steam do? It does two things. Firstly, it reduces the partial pressure of the vapor inside the column, and secondly, it also supplies the latent heat which strips the vapor from the reduced crude oil. So, therefore, then along with the vapor the steam rises. The column top temperature and pressure should be maintained such that the steam does not condense within the column. It goes to the condenser, gets condensed, and then in the reflux drum generally there is a steam which is collected below the reflux drum. In this particular case we usually have a boot leg which is called, where the steam is collected, the water is collected and that is drawn out from there. Well, after this the next thing which we have is the feed zone. Now, in the feed zone it is important for us to remember that the feed, it can be either a vapor feed, it can be a liquid feed, it can be a vapor liquid mixture as well. This feed, it enters through a feed nozzle here, and this particular portion, this is also known as a flash zone, because part of the feed while it enters it vaporizes here. Now, for increased thermodynamic efficiency, what do we desire? We would desire that the feed condition will be same as the column condition at the feed plate. Definitely we will desire that, but it is definitely it is very difficult to have it. We would not desire to have a subcooled liquid or a superheated vapor feed, definitely, because there will be some heat exchange and some that will definitely decrease the amount of enrichment that we get. So, therefore, we would either want a partially vaporized feed or a saturated feed at the column temperature. This is achieved by means of a preheater just before the or in the fitted in the feed line, where the feed can be preheated. We can use the hot bottom product to heat the feed in the preheater. One other thing also, it is important for you to remember that generally the spacing above the feed tray is higher as compared to the spacing of the other trays. This is something you need to remember when you will be deciding the column height. Both the feed tray, and this also applies to the bottom tray. For both these cases, the feed tray as well as the bottom tray, the spacing is higher as compared to the other trays. This reduces the liquid entrainment by the vapor. Well, this was the basic arrangement. I have discussed the overhead, the arrangement for the overhead section, the bottom section and the feed zone. These are the basic arrangements. In the normal arrangement, in the complex configurations, we have several other things. We need to consider the side stream draw, we need to consider multiple feeds, etc. Also, there is an external refluxing arrangement. These things we are going to discuss in the next class. This much for today. Thank you so much.